Having counted number of reflexive binary relations, let us count number of symmetric binary relations. Recall the matrix. For that example, we saw that it was like this. There are other elements 1, 2, 2, 1, 1, 3, 3, 1, 2, 3, 3, 2. So when we count symmetric binary relations, so the definition says if AB is present, then BA must be present. If AB is present, then BA must be present. So in some sense, if you take this element, its counterpart is forced. If AB is included, then BA is forced to be included. So what we will do, you leave this part diagonal, because for diagonal elements AB and BA are one and the same. Any subset from this is a symmetric relation. So empty set or just 1, 1 is symmetric, 1, 1, 2, 2 is symmetric, 1, 1, 3, 3 is symmetric, or 1, 1, 2, 2, 3, 3 is symmetric. So any subset from this is symmetric. So any subset from the set 1, 1, 2, 2, 3, 3 is symmetric. Let's focus on non-diagonal elements. So what we will do, we will group them like this: 1, 2, 2, 1 and 1, 3, 3, 1. Basically AB and BA. In general, I'll include AB and BA where A not equals B. If A and B are same, then it is diagonal elements. We are focusing on non-diagonal elements. So like this you are grouping them. So how many non-diagonal elements are there? There are n square minus n, but we are grouping them, so which means there are n square minus n by 2 pairs are there. So the size of this is n square minus n by 2. Now you take any subset from this. You take, now you can see this one as say B1, say B2. So this one as B n square minus n by 2. So now this basket is 1, 2, 2, 1. This one is 1, 3, 3, 1. Like that, there are n square minus n by 2 baskets. Now you can choose any subset of these baskets. You choose nothing, empty set, that's symmetric. You choose this one and this one, that's also symmetric. So number of subsets on n square minus n by 2 baskets is how much? 2 power n square minus n by 2. Now along with this, suppose the basket that you choose is say B1 and B2, then you will have 1, 2, 2, 1 and 1, 3, 3, 1. With this, I can union any subset from the diagonal set. So which means you can associate 1 1, 2 2, 3 3 or just 2 2. Okay, which means number of symmetric binary relations is 2 power n square minus n by 2. With that you can associate any subset from the diagonal. So this is precisely the number. On simplification you get n square minus n plus 2n by 2, which is n square plus n by 2. That will tell you 2 power n into n plus 1 by 2. So there are this many symmetric binary relations on a set of size n. So I repeat, if you look at this A cross A, we look at diagonal elements separately and non-diagonal elements separately. Non-diagonal elements, we are grouping them like AB and BA. Why? Because when we try counting symmetric relations, if AB is included, then BA is also included. So it is enough if you focus only on the lower diagonal part or the upper diagonal part. So if you group them, you get to see that there are n square minus n by 2 baskets, and any subset of this together with a subset from this is an example symmetric relation. So how many subsets are possible on n square minus n by 2 baskets? This many. With that you can associate any subset. I can associate empty set, or I can associate 1 1 or 2 2, 3 3. So this many relations are possible. So number of symmetric binary relations is 2 power n into n plus 1 by 2. On the similar line, let's count the number of antisymmetric binary relations. Here again, you take any subset from this, that's an example antisymmetric relation, and the other part one has to be careful. If you take 2 1, then I should not take 1 2. Otherwise what will happen, if 2 1 and 1 2 are same or included, then they both have to be same, but they are not. Let's group them again. 1 2 2 1 and say 1 3 3 1. So in general, AB BA. Now there are 3 possibilities for a basket. Either 1 2 is included, or 2 1 is included, or none. None of them are included. Both cannot be there. If both are there, then it is not an antisymmetric relation. We are trying to count antisymmetric relations. Which means in general, if you look at a pair AB, either AB is present, or BA is present, or none of them are present. So for each pair there are 3 possibilities. For each A comma B belonging to non-diagonal set, there are 3 possibilities. So now, how many such possibilities are there? So number of such possibilities or number of such subsets is 3 power n square minus n by 2. For each basket you have 3 possibilities. Number of baskets is n square minus n by 2, so you get 3 to the power n square minus n by 2. Now along with this, together any subset from the diagonal set is an example antisymmetric relation. So which means number of antisymmetric relations is precisely 3 power n square minus n by 2 times 2 power n. So from the contribution from the diagonal is 2 power n. Contribution from the non-diagonal part is 3 to the power n square minus n by 2. The reason is you get n square minus n by 2 baskets, and each of them has got 3 possibilities. Either 1 2 is included, or 2 1, or none. I am using either or, which means the possibility of having both is not considered. Okay, and so that precisely tells you that if you take this, you don't take this, or if you take this, you don't take this, or there is a possibility that none are included, neither 3 comma 1 nor 1 comma 3. So when we say none, it is neither 1 comma 2 nor 2 comma 1. And how many such possibilities are there? Now how many such subsets are there? It is 3 power n square minus n by 2. Along with that, choose any subset. So you get this many antisymmetric binary relations. Okay, very interesting part. One can actually list, for this one can list how many are there, and in general the count will tell you that this many antisymmetric relations are there. On the similar line, one can count asymmetric, and one can also associate more than one property, meaning number of reflexive symmetric relations, number of reflexive antisymmetric relations, and such questions one can ask and experiment. And all these varieties and other form of counting, and you find them in my scribe, you go through it, and more on this, couple of questions related to this, variants of this, all that we shall see as part of our problem session.